Zo. Als het goed is zijn we live. Kan iemand bevestigen dat je mij en kunt zien en kunt horen?
Ik kan bevestigen.
Je mag het chatten.
Ja.
Ja, krijg je al een reactie? Ik nog niet. Yes, helemaal goed. Nou, dan ga ik mezelf nu nog even muten. Over 14 minuten kom ik bij jullie terug. All right, so we're almost ready. I'm wondering, Simon, are you there?
Maybe what I'll do is I'll get Sander, Otte, and Simon on a.
So they are online now, both of them.
Okay.
All
right. Let's go with that then.
Okay. Welcome, everyone. Good afternoon. Physically present or digitally present. These are rather unconventional times, so I'm really glad we can make it work this way. So yeah, welcome at my master's thesis defense, and let me start from the beginning. So when I went looking for a master's project, I really wanted to do something with quantum mechanics. And why? That's because the quantum world, which is the world of the really smallest elementary particles, this world is nothing like the world that we experience around us. And the last 7 months, I've been fortunate to be introduced to the fascinating world of superconducting quantum bits. And today I will take you on a tour through them. Specifically, I'll present you the breakdown of the rotating wave approximation between in sideband transitions between a superconducting qubit and cavity. Well, that is quite a mouthful, but I will walk you through it. And actually, this title comes from the main result of my thesis. Actually, the main goal of my thesis is that we have a qubit and we have a cavity, and we want to control the coupling between them. We want to control the interaction between them. And we want to do that with sideband transitions, and that is in its turn a part of the larger project to realize the atomic beam experiment on a chip and to control the photonic state of that cavity on the chip. Okay, again, a lot of terms. So let's divide this. What I will present to you today is why is this atomic beam experiment so interesting, and why should we want to do that on a chip? Then the setup, I'll discuss the superconducting qubit and the cavity, how we can use sideband transitions for this coupling, and lastly, I'll show 2 of my results. All right, so let's start with the atomic beam experiment. In this experiment, we have a source which produces atoms, and these atoms are shot through a cavity which consists of 2 highly reflective mirrors. And if this atom goes through the cavity, it can exchange energy with this cavity, and this energy is then transferred in the form of photons. When the atom leaves the cavity again, we can pick it up by with a detector. And this experiment, why it is so interesting, is what we want to do as physicists is to really understand how nature works. And the interaction between matter and light is one of the fundamental interactions that we see in nature. And if we really want to understand how that works, then we really have to look at it at the very smallest scales. So that is when a single atom meets a single photon, that is a single particle of light. Okay, so that's the atomic beam experiment. Then I said we want to do that on a chip. So why on a chip? The main advantage of a chip is that the atom and the cavity are both represented by an electrical component on this chip. And these electrical components, we can fabricate and design them totally as we wish. So we have full control over the different parameters and shapes and all. So that is really advantageous. And it's also the different elements that I use in my project. These form the leading architecture nowadays for quantum computers. And probably most of you have heard about quantum computers. These use a totally new way of processing information, which in theory would make them be able to do some computational tasks much faster than any supercomputer that we have today. And within these quantum computers, it is the photon that is exchanged between an artificial atom and an artificial cavity. It's these photons that are the information that is processed in a quantum computer. Okay, so let's dive into this chip. So within this chapter, I'll discuss three things. So first, the different circuit elements that we have. Then sideband transitions and how we can use them to control the coupling between the different elements. And I will discuss two different models that we use to simulate the qubit with. Okay, let's start with the different circuit elements. So I said that these the cavity and the atom from the original atomic beam experiment are represented by an electrical component on a chip. The cavity is represented by a coplanar waveguide resonator, which we can model as just a harmonic LC oscillator. And this oscillator can contain photons, and it is because it can only contain a discrete number of photons, so 0 or 1 or 2. We have discrete energy levels. So we can measure the system in this energy level or in this energy level, but not an energy in between. That's the cavity. The atom is represented by a so-called transmon qubit. And this is basically the same electrical circuit element, but where we have a nonlinear Josephson junction instead of a linear inductor. And this transmon qubit has the characteristic that its energy levels are quantized as well. All right. So on a chip, these the cavity and the qubit, they are coupled to each other through this capacitance. And through this capacitance, they can interact. They can exchange energy, but they can only do that when the excitation energy of the qubit is equal to the excitation energy of the cavity. And in this case, we see that they are not equal, and there will be no oscillations of energy between the qubits and the cavity, because at this height, there is no cavity level. We can visualize this system in another way, and we will use this so-called energy diagram more within this presentation. So the height of these levels represents the amount of energy that the system contains. So for example, over here, we have the situation where the qubit is in this ground state and the cavity contains one photon. And this state, for example, the qubit has one excitation and the cavity has 0 photons. We see because this level is higher, the qubit excitation energy is higher than the cavity excitation energy. And as I said, in this case, they cannot exchange energy. So there are no transitions between these two states. This represents then in the original experiment, the atom being outside of the cavity. Because if the atom is outside of the cavity, there is no interaction between them. But on our chip, the cavity and the artificial atom, they are fixed. You cannot move them. You cannot shoot the qubit through the cavity. So we have to do something to make that interaction possible. There are two ways. So one way is to use a so-called squid device, and this squid consists of two transmon qubits in a superconducting loop, and what we can do is to apply a magnetic flux through this loop, and when we do that, we can change the excitation energy of the qubit. So we can, for example, go to this state, and then we see that both levels have equal energy, and there can be transitions between them. The disadvantage of this method is that this circuit is very sensitive to flux noise, so we will not be able to keep this level at exactly the right height. The second method is the one that we use with so-called sideband transitions. And to induce these transitions, we apply a drive to the qubit. And this drive is essentially just a voltage source. And if we apply a voltage signal with just the right intensity and just the right frequency, that it can span the energy gap between these two energy levels, then there will be transitions between these two states. And if that is the case, then that represents the atom being inside of the cavity. And I can visualize these oscillations by this graph. So this is a simulation of these sideband transitions. On the horizontal axis, we see the time, and on the vertical axis, we have the average number of excitations inside the qubit and the cavity. And we see that if we turn on the drive over here, we start with the qubit containing one excitation and the cavity containing 0 photons. And if we turn on the drive, we see that the energy flows from the qubit to the cavity. And after, in this particular case, after about 1 microsecond, we see that the energy is maximally transferred between the qubit and the cavity. And that energy exchange occurs periodically over time. And it is now the rate at which these transitions happen that determines how strong our effective coupling is in our atomic beam experiment on the chip. So the rate is important. Okay. So what this means is that by just turning on a drive, we can induce transitions. So when we turn on the drive, that mimics the atom going into the cavity. And by turning off the drive, we can mimic it leaving the cavity again. So by just turning on and off the drive, we can mimic any arbitrary setup of this as we wish. So that is really the strong point about these sideband transitions. Okay, let me go to the models of the qubit. For the people at home, it's going to be a little bit mathematical now, but don't be scared. Bear with me. I will take you through it. So if we have our qubit and this capacitance is really large, then we can approximate the transmon qubit by a so-called Duffing oscillator. And the total energy stored inside the qubit is then given by this Hamiltonian. Okay. What people then often do is to simplify this last term with the fourth power. And inside this term, what these qubit annihilation and creation operators represent is a field rotating one way at the qubit frequency or the other way. And if we write out all the terms in this fourth power term, we get all B's, and we have terms rotating at 4 times the qubit frequency, at twice the qubit frequency, and terms that are not rotating at all. And I can visualize this for you by just this arbitrary signal that I've drawn. So you see the larger trend that it has. You also see these very rapid and small oscillations. Well, if we are interested in only time scales like this, then all these small oscillations, very fast oscillations, they practically do not matter for our solution. And approximating then this signal by this blue line through it, that is called the rotating wave approximation. And that's exactly what people then do over here. They discard all the fast oscillating terms. And if we do that, we arrive at the so-called Kerr oscillator. So these are models for the qubit, and the total energy in our system is then given by the qubit Hamiltonian, the energy stored in the cavity, the energy in the interaction between the qubit and the cavity, and in the drive. Well, in the drive, what people often do is to apply similar rotating wave approximation. And they approximate this term by this. So you remove all these fast oscillating terms as well. But in my thesis, I show that in the case of sideband oscillations, this is often not a good approximation. So what I use is this form. Okay, that was a lot of math. The main message for everyone over there is that the Duffing oscillator is an approximation of the transmon qubit, and the Kerr oscillator is an approximation of the Duffing oscillator. And what people in literature often do is just start right away at the Kerr approximation. And during my project, I asked the question, is this also a valid approximation in our case of sideband transitions? And that brings me to the next chapter, the results. I have 2 results for you. So the first are simulations where I compare the Duffing oscillator to the Kerr oscillator. And second, I have real measurements of these red sideband transitions. Okay, let me start with the simulations. So comparing the Duffing oscillator to the Kerr oscillator brings me to this graph. We have simulations here of both of them, and on the horizontal axis, again, the time scale, and on the y-axis, we have the probability that the qubit is excited and the cavity contains 0 photons, minus the probability that the qubit is in its ground state and there is 1 photon in the cavity. So these states represent the states that are involved in exchanging energy between the qubit and cavity. And if we compare the Duffing oscillator to the Kerr oscillator, we see that the Duffing oscillator has sideband transitions like this, and the Kerr oscillator, they go like this. And you see that the oscillations in the Duffing oscillator occur much faster than in the Kerr oscillator. And this example is just for one particular drive intensity. But if we do these simulations for more drive intensities, then we see that difference, that we see that in the entire range. And specifically, the transition rate within the Duffing approximation is almost 3 times faster than in the Kerr approximation. And that is a significant difference, especially if we think about it, that the only difference between the Kerr and the Duffing oscillator is that we, in the Kerr approximation, we removed all these fast oscillating terms. And this result shows us that these fast oscillating terms cannot be neglected in the case of sideband transitions, because they have two significant effect on the transition rate. All right. Then we're interested in, does nature really work this way? So for this, for the measurements, I have to explain real quickly how we have measured them. So over here we have a photograph of the chip. We have the transmon qubit over here, and over here there's the cavity, and we apply a probe tone to the cavity. And this probe tone has a certain intensity and a certain frequency, and it is that when this frequency of the probe matches the frequency of the cavity, then the signal is transmitted. And if it's not at resonance, then the signal is not transmitted. Okay, so if we vary this probe tone, so that is the frequency of that probe tone, so that corresponds to the height of this arrow. If we make that from smaller to larger, we observe a graph like this. So we have the probe frequency, the height of the arrow, and the how much of the signal is transmitted. We get a Lorentzian curve like this, where at the cavity frequency we get maximum transmission. Now, if we add to this the drive with a certain frequency, if that frequency is the right frequency, then we obtain a curve like this. So what happens? We vary the height of that arrow again, the probe frequency, and when that frequency matches this transition, so that's over here, then the drive immediately depopulates the cavity and brings the system from this state to that state and brings the energy to the qubit. And if we then fit a model through this measurement, we can extract from that fit the sideband transition rate, so the strength of the sideband coupling. And yeah, the reason that we observe this dip is because if the qubit is excited, the excitation energy of the cavity is not equal anymore to this. So the probe is then not at resonance anymore with the cavity. Okay. Then I have the results over here. So these dots are the measurements. We have the drive strength and we have the transition rate. And these are the measurements, and these pluses, they are simulations with the Duffing model. And what we see here is that the measured transition rate is approximately 57% of the simulated transition rate. So that is roughly a factor of 2. But if we think about it, if we think about the model that we use to do these simulations, that is actually a very simplified version of reality, and that we've come with only a 43% difference. That's actually a very good result. Moreover, the sideband transition rate that we've measured here, that really gives us the effective coupling strength that we need for our atomic beam experiment. So we can immediately use this result. Well, that brings me already to the conclusions. So what we've seen is that we can use sideband transitions induced by a drive to control the effective coupling between the qubit and the cavity just by turning on and off the drive. We've also seen that the sideband transition rate within the Duffing approximation is significantly higher than within the Kerr approximation. So that shows the breakdown of the rotating wave approximation, which is the title of my thesis. And we have seen that the measurements of these sideband transitions, that they give us the coupling strength that we need for our experiment. Well, my project has ended here. This was my journey, but the larger project is not done yet. So let's take a look what's up ahead. So of course, the thing that one of the next steps is performing this atomic beam experiment or any similar experiment that we want, perform that on a superconducting chip. Then, also an important next step is to translate uncertainties within our measurements to the uncertainty in the measured transition rate. Let me explain that real quickly. So we have our measurements and we fit a model through that, and that gives there's a certain uncertainty within that fit, and we also have that for other measurements on which we base our model. And if we translate those uncertainties to the error bars within the error bars of our measured transition rates, it might be that this difference between the simulations and the measurements, that difference becomes smaller, and that it is actually within the error range. But we have to check that. And lastly, of course, we want to be able to predict this coupling strength as well as possible. So also we can take a look, what physics do we still need to add? What can we add to make the model better and more effective to predict this transition rate even better? All right, that has brought me to the end. I want to give a major shout out to the team, who has been always very friendly and helpful, and especially to my supervisor Gary and to my mentor Byung Mo, and all the other people that have helped me. It was an amazing journey, and with this I would like to thank you for your attention. Thank you very much, and if there are questions, I'm happy to answer them. Thank you. And yeah, now there's the time that you can type questions, and I will answer them. Go ahead.
I just got a message from Simon that his video stream is choppy.
Oh.
And that he's about 5 minutes behind.
Okay.
Maybe
we have to wait then a little bit more. Okay, some people have already watched GM because I see applause. Okay, thank you very much.
Oh, we can applaud.
Yeah. Thank you. Okay, I have a question from Snike. Thanks for the presentation. When comparing Kerr versus Duffing, you graph some probability minus another probability. Why is it significant if these quantities differ? What is this quantity? That's a good question. Let me get back to it. So I have the probability that we measure the system in one state or the other. And these states, E0 and G1, they correspond, let me get to this, they correspond to these states. So I measure the probability that we measure the system in this state minus the probability that we measure the system in this state. And if that probability, if there are transitions between these two states, we obtain those oscillations within one graph. And I showed the graph in that particular quantity because then with that quantity I can capture both of these graphs in one graph, and then I can compare multiple models with each other. So I hope that answers your question. Okay, thank you very much, everyone. Is there another question someone likes to ask? Let me get a sip of water. Ah, great. I answered your question. Beautiful. So probably if the connection is a bit lagging with some people, then have to wait a little bit more.
Yeah, let's see.
Right, I have a question from Matthijs. If the Duffing model shows higher transition rates than the Kerr model, and you measure lower rates than the Duffing model predicts, isn't the Kerr model actually the better one? That's a very good question. Yeah, you would say that. But if we do this, the derivation of this this electrical circuit, then we first arrive at the Duffing oscillator, and then by more approximations at the Kerr oscillator. So the Duffing oscillator is mathematically always a better approximation of the qubit of the transmon qubit than the Kerr oscillator. That when comparing them to the measurements, maybe the Kerr approximation would give a better result, but there's one step in between that I haven't showed you. But we have to base the drive strength on simulations. So and the simulations we've done those with the Duffing oscillator, and these points would probably be on another on a bit other line when we did that with the Kerr approximation, because the Kerr is an approximation of the Duffing approximation. But yeah, good question. But I cannot agree that the Kerr is would be a better model to model this transmon qubit. That's it.
Let me rephrase actually this question.
Okay.
Purely on a pragmatic level, if I did just use the care model,
Mm-hmm.
it looks on the first sight, like Matthijs pointed out,
Yeah.
that it would agree with your experimental data.
Yeah.
Regardless of whether or not you think that it's a better theoretical model or not.
Mm-hmm.
But you also then pointed out that this graph is more complicated than it looks.
Yeah.
Because both the x and y axes are calibrated by, well, the x-axis is calibrated by model parameters numerically, and those model parameters, those models have an input which you've independently calibrated.
Exactly.
There are other parameters which also have experimental error. So, but you didn't try, say, performing the entire calibration routine with the care.
No, that's true. I haven't done that calibration on the care oscillator. That's true.
Okay.
So yeah, we can try, and maybe it gives a better prediction, and then yeah, we have to think about what that then actually means. But I would say that to bring these closer, that we have to first take a look at other effects, other physics that that play a role in these sideband transitions. Okay, I hope that answers your question. So I have another one of Thomas. Good presentation, thank you very much. In your presentation, you mentioned that you used rather cold fridge. How did that relate to your research? Why did it need to be cool? Okay, so yeah, we need a really cold fridge, and that the reason for that is the following. So we're measuring individual excitations, that is individual photons, or in the case of the transmon qubit, individual Cooper pairs, or those are paired up electrons. And because these particles are so small and their energy is so small, we have to get all the energy from the environment as small and low as possible, so that the energy of these individual particles does not drown in the sea of thermal noise. Because higher temperature means a lot of vibrations everywhere, and a lot of energy. So we bring the fridge down to 10 millikelvin, which for the people who do not have a feeling for that is extremely cold. And that is so room temperature is 293 Kelvin. Water freezes at 273, and we're at 0.01 Kelvin. So it's extremely cold. Yeah, so that so that we are able to measure these single excitations. That's why we needed to make it so cold. Thank you for your question. I have another one from Inge.
Other questions?
Yeah.
A lot of questions.
Might have missed it, but do you have any suggestions what is currently missing in the models? What could explain the difference between the experimental results? That's a very good question. So I tried multiple things, and they're mostly mathematical things. So, for example, this term comes from a fourth order Taylor expansion of a cosine. I tried with a sixth order Taylor expansion. That didn't help, or at least negligibly small difference. I tried, for example, if you look closely, there's another cavity over here, and in our model we do not include that. But in fact, it does play a role. But also the effect of this cavity, second cavity, is negligible. And I tried some other things, but until now I've not been able to find that specific thing that makes the simulation rate and the measured rate get close enough together that we can say, well, we're exactly on the right track. Okay. Then, mother, Nederlandse Wikipedia. Lange tijd zag men in Josephson Junctions een veelbelovende technologie om er snelle computers mee te maken. Tot dusver is die technologie niet doorgebroken. Vooral door de technische moeilijkheden rond de koeling die nodig is voor supergeleiding. De vraag, is dat nog actueel of zie jij mogelijkheden voor de Josephson Junction om die voor een quantumcomputer te gebruiken? Okay, so the question, let me translate to English. So Josephson junctions for a long time were very promising technology for fast quantum computers, but the main difficulty was a technical one around the cooling that is needed for superconductivity. And is that still currently the difficulty, or do you see the Josephson junction as a useful part for a quantum computer? Okay, the first question is that still difficulty to get down to superconductivity? Superconductivity indeed occurs in some materials below a certain threshold. And what superconductivity is that electrons, they pair up and together they can flow, and they can flow without any electrical resistance. And a Josephson junction, I'll have a picture of this. This is superconducting material and this superconducting material, and they're separated by an insulator. And these Cooper pairs, they cannot electrically be conducted through this, but they can, if this is thin enough, they can tunnel through the other side. They can jump to the other side. And to get this material superconducting, in the materials that we use, we have to get down to 4 Kelvin, and that's not a problem because our experiments happen at 10 millikelvin, and for superconductivity we need 4 Kelvin. So technology has come far enough that is not a problem at all. Whether Josephson junctions are a good part for quantum computers, I think so. So this Josephson junction is, let me get all the way back. So this Josephson junction is part of the transmon qubit, and the transmon qubit is really the still what is most promising for the quantum computers. The difficult thing now is dealing with all resonances in cables and calibrating all sorts of parameters, and that's mainly the difficulty now, but not superconductivity. All right, I hope that answers your question. I have a question from Leon. Did kinetic inductance play a role in the resonator? That is true. So let me then go to this one again. So we have these Cooper pairs. They can tunnel to the other side, and where the energy stored in this junction comes from the momentum of these charge carriers, because electrons are charge carriers. And if we look at the wave function, and you're a physicist yourself, so you should be able to understand that the wave function decreases exponentially over this insulator and also from this other side. And that means that if we have a current through the insulator, so the Cooper pairs go from this side to this side, if the probability to measure them over here or over here is higher, that means that over here we have the lowest probability to measure them, and their momentum over there has to be the highest. And you can compare that to, for example, a flow of a fluid that goes through a more narrow, a narrow tube. That at the most narrow point, the stream flows fastest. So yeah, that is kinetic inductance. I have another question from my mother. Technische moeilijkheden rond de koeling die nodig is voor super. Oh, that is still the old question. Levert jouw onderzoek daar dan bijdrage aan specifiek? Yeah, good question. So does my research contribute to realizing a quantum computer with transmon qubits? So I say it could. I'm not sure how you could do that exactly, but so this my project has been part of controlling of the larger project to control how many photons are stored inside this cavity, and to control that just by shooting atoms through it on a chip, shooting atoms through it. And if we are able to control the number of photons inside that cavity, you could use that for information processing, which is basically what a computer does. So these elements, coplanar waveguide resonator and a transmon qubit, is what they also here at the TU Delft, what they use to build a quantum computer. There are also other materials possible to use, but this is at this point, I believe, still the most promising. So yeah, I've contributed to that as well. Okay, so I think those were the questions. I don't see any more questions. So maybe room for one last. All right, then I want to thank you all very much for your attention and for all your questions. I hope you've enjoyed it and learned something from it. And yeah, thank you very much. That's it. Okay, yeah, I'll close this streaming. Thank you. See ya. And
yeah,